Hey guys, we want to go ahead and finish up chapter 16 today. It's not much information left, but we've already talked about KVP in part one and part two. Part one actually telling us about the way that KVP actually affects the beam itself, knowing that there is, as we increase our KVP, we're actually increasing the number of x-rays being created. Therefore, your patient exposure actually is going to go up. And the second part talked about the 15% rule, that we did a compensation for the number of x-rays being increased by increasing KVP. We can actually reduce the mass in half, thereby actually reducing patient exposure dramatically, because we know mass is the primary controller for patient exposure. So today I want to talk a little bit about how this all ties together and how this relates to our patient exposure. So let me share my PowerPoint if I can find it and get it going. And there it is. All right, let's see. We're going to go to the current slide. The current slide starts on page, in your book, it starts on page 254. It says it's called optimal KVP, and I added the word patient exposure question mark. How? How does this optimal KVP, higher KVP, actually affect your patient exposure? And I say higher KVP, optimal KVP, because remember, we talked about there being a minimum KVP. Minimum KVP only ensured that you had penetrability, that you have penetrated the thickest portion of the anatomy. Now, optimal KVP is the highest KVP that you can go and still produce an image with good scale of contrast, because remember, higher KVP stretches your scale of contrast. We don't want to stretch it so far as that we can't see the various grays and the difference between them. We want to maintain that contrast to some degree, but yes, we do prefer long scale contrast to a degree compared to a black and white high contrast image. So on page 254, at the very bottom is where it starts talking about it. It says optimal KVP. On the PowerPoint, is there a limit? It says as shown below on page 255 in your book, figure 16.4, with conventional film-based radiography. I know you get tired of seeing that, but you really have to be able to appreciate the era of imaging that I came from, and most of the faculty came from, or were at least exposed to it, was that we still did film screen-based radiography. Both lower and upper limits restricted the range of KVP. Too high KVP would actually overexpose the image. Now for digital DR, quantum model and penetration requirements still set a lower limit. Quantum model, by definition, simply means that the image did not receive enough x-rays, enough energy, so not enough KVP, and not enough mass, so you get this speckled look. And obviously, if you have to get your minimum penetration, as always, you have to penetrate. And when you know that you have penetrated the anatomy, the IR is actually receiving that energy, that KVP. DR systems love energy. Usually, the more energy you give it, the better your pictures are actually. But there is a lower limit on digital radiography, so that minimum limit on KVP has to be hit in order to produce a good image using digital radiography. As long as the KVP is above the minimum, the computer can resolve to a good image. Okay, so that's one bullet I want to stop on for just a second. As long as the KVP is above the minimum, and again, remember that we have ensured that we've got penetration. That's the minimum. We have exposed the patient and penetrated the thickest portion of that particular piece of anatomy. We're able to see if it's bone work. We're able to see the thickest portion of the bone, and we're able to see the bony trabecular pattern throughout the entire image. Therefore, you do have a good image. On page 255, it kind of speaks on this. It says, As long as the KVP is above the minimum required for adequate penetration, top of 255, the computer can resolve a good image. The KVP range is more limited with conventional, obviously very much with conventional film radiography. Since the use of high KVP low mass technique reduces patient exposure, and that's what we're going to be talking about. That's what this third part is all about. Again, since the use of high KVP low mass does reduce patient exposure, it is difficult to find any justification or argument for lower KVP settings that barely meet the minimums listed on that table that we talked about on table 16.1. It talks about the advent of the computer-based systems which force radiographers to rethink their definition of what constitutes optimal KVP or recommended KVP for each body part. It says we will define optimal KVP as a level of KVP well above the minimum required to sufficiently penetrate, which strikes an appropriate balance, we talked about that, between saving patient exposure and preventing excessive scatter radiation. We talked about scatter radiation somewhat in earlier lectures, and remember, scatter radiation is not being produced by the higher KVP. The question was, why did we have to set our higher KVP? So you're doing an exam. Why are you going up so high on your KVP? Well, it's because of the patient size. So the larger your patient, the larger the body part. It's the thickness and the atomic number of that particular body part, the tissue, the bone, whatever your imaging contrasts. It depends on the atomic number and the actual thickness of the patient that produces more scatter. It's not necessarily the higher the KVP. We have to, again, get to that minimum penetration. And so in order to get to the minimum penetration, and as our population is leaning more towards the side of morbid obesity, that's the reality of our world, then we are being forced to use higher KVP, but keep in mind also, we just said that the DR, the computer and digital world of radiography, actually likes higher KVP. It likes energy. The more energy it receives on the plate, the better and the more information it can produce in your images. Okay, so optimal KVP, again, I'm still on page 255. It says that patient exposure in the 15% rule. For digital radiographer, we've already defined it is defined as, we've already defined optimal KVP. It is defined at a level of KVP well above the minimum required for sufficient penetration, which strikes the appropriate balance between saving patient exposure and preventing excessive scatter to the IR. To achieve a particular exposure at the image plate receptor, patient exposure is saved whenever KVP can be increased instead of mass. KVP, higher KVP, is better for our patients instead of increasing our mass to get a higher or larger exposure. Why? Why is that so? Well, think about this. You've done a patient at 20 mass at 70 KVP, and very few got through. So now we were doing it at 40 mass, and we're keeping it at 70 KVP, same KVP. All of them are still getting what? Absorbed by the patient. So you're really not changing anything. And remember that one statement, there is no level of mass that can compensate for an underexposed patient, an underexposed exam. So nothing you can do with mass can compensate for underpenetration. It has to be the KVP. Higher KVP does generate significant scatter radiation when the body part is not large enough to produce substantial scatter in the first place. There's a little problem right there. So we do want to set a high KVP in the DR digital world, but we don't want to set it so high that it produces nothing but scatter and that it's not necessary to be that high for the body part that you're trying to penetrate. In other words, don't use 90 KVP on a finger. It's unjustified, it's unwarranted, and it will produce a lot of scatter, plus it will be what we consider overexposure, or in the DR world, they call it oversaturated. So the majority, if you're using too high a KVP for that particular body part, then your actual plate is receiving more transmitted all the way through with less attenuation. They're too strong, so the little finger, if you're doing at 90 kVp, it's not going to be able to attenuate any of those x-rays. So you've actually given the plate too much energy. Compared to large body parts and large field size, both of those are going to create to increase your amount of scatter. So it's a larger body part and a larger field size. KVP is only a minor contributing factor for the production of scatter radiation. So the two main components that are creating your scatter is going to be, first of all, again, the large body part, a lot more tissue for those x-rays to interact with and to bounce around and to create more Compton interactions. And obviously a larger field size. As we increase our field size, open up our collimation, what is it actually doing? It's using more of those off-focus x-rays. We're getting further away from the central ray, and that angle is going to actually cause you to have more scattered events to occur. Okay, so on page optimal KVP, page 16-2, that's the figure. 16-2 is on 256. Table 16.2, it lists several estimates of the contribution of KVP to the patient's entrance skin exposure when the 15% step increase in KVP is made. So in other words, they're taking measurements as we're making incremental steps of 15% increase in our KVP, and at the same time reducing our mass into half. They're taking actual readings and put it on this grid, this graph for you, this table, and it's showing you what's happening to the ESE, which is entrance skin exposure. So it's showing you that there is a reduction as we increase our KVP. The majority of that reduction obviously is going to come from us being able to reduce the mass value by half. That's already reduced the patient exposure by 50%. And then they take that, whatever is over the 50%, and they're going to say that that percentage is because of a higher KVP, and it's a very small amount. So there's a very small amount of patient increase of an exposure when you're using higher KVP, which it should stand for a reason, because as you go higher in your KVP, you're actually pushing more of those x-rays through. But we're talking about skin entrance. So we're talking about all these x-rays are actually being able to get through the skin. So that's why they use the skin entrance as a measurement there, because you're actually measuring all of the x-rays, not those necessarily that are being pushed through the patient completely and become part of the image production, but actually patient exposure, that's starting at the level of the skin going through. And it says, as explained in Chapter 10, this is due to an increased number of brimstone lung x-rays produced in the anode at a higher KVP. In Table 16.2, these amounts range from 28% to 38% increase in patient exposure. I'm going to go over that in just a second. So this table on page 256 again, and I'm not sure if you guys are even able to see my mouse or not. That was one thing I needed to look up. But at this, on page 256, using optimal KVP, it says percent increases in entrance skin exposure due to 15% step increases in KVP. So our first exposure, 1, 2, 3, 4, and then there's another from a clinical unit that had 3 exposures. But the idea here is to look at your second exposure compared to your first. The first exposure, 70 at 16 mass, gives you a MR reading of 146. So just by us taking that 16 mass, cutting it in half to 8, and increasing our KVP by 15%, which turns out to be 81, we now have a measurement of 98.1% of MR units measured. Well, that is a 67% of the difference from the 2 exposures. So we know that by reducing our mass from 16 to 8, that halved it. So we take 50 away automatically. That leaves us with 17. 17% of the other 50% of the total of the exposure. So we say, what part of 17, what percent of 17 is that other half of the image exposure, of the exposure, and it's 34. And going down to number 3, you're comparing that to the same exposure. As we reduce our mass down in half again to 4, we've increased our KVP by 2 steps now. We went from 70 to 81 to 93. Look at the MR units that it measured, 64.5. We minus the 50%, so we got 16. 16 is 32% of 50. Y'all get the gist of this chart. This is really important, and it's really cool how they did that. I just noticed that this came from the University of North Carolina in Chapel Hill. I went there many times for several workshops. It's a fantastic program. Anyway, our last step is a very high KVP. We've gone up 3 steps from 70 to 105. We've taken our original mass of 16, and now we're at 2. The measured MRs is 41.4. And at 41.4, the difference between that and the previous one above it of 64.5, you are now at 64%. So we have 14 over, and that 14 we were saying that is increased by, due to the increase of KVP, 14 of the other half of the image, because half of it's already been removed, or half of the total exposure has been removed because of the reduction of your mass by half. So that's 28%. Does everybody get that? Focus on this chart. It's really cool. It's got a lot of great information on it. So optimal KVP, we conclude that a 15% step increase in KVP on average increases patient exposure by about 1/3. So by us simply going up 1 step, 15% in KVP, and halving our mass, we've actually reduced the patient exposure by 1/3, which is that's substantial. And it's telling you how we did that. It says, since halving the mass cuts patient exposure by 50%, automatically, it's directly proportional. You go up, you double your mass, you double exposure, you half your mass, you half your exposure. The net result for applying the 15% rule to reduce mass will be patient exposure averaging about 67% of the original, always a net savings in patient dose of about 1/3. Again, a 1/3% reduction in overall patient exposure by applying the 15% rule one time. Patient exposure is saved whenever KVP can be increased instead of mass. So we are now in the world of technology where the systems can handle higher KVPs. We encourage you guys to use higher KVPs for this reason. If you increase your KVP roughly by 10%, and you remember the 2 charts in this chapter, these 2 tables, I think it was 16, I was on the front of the book. Let's see where I'm at. I'll find it for you real quick. On page 252, table 16-1, compare it to the table on the back of 258, and you can see that they actually did an increase of 10 in the KVP. And by doing that, these are new digital exposure techniques that you can be using in the department. You are now reducing the patient exposure by 1/3. Optimal KVP guiding factors. These are listed on page 258. It says higher KVP does not generate significant scatter radiation in smaller body parts. I feel like I've skipped something. Okay, yeah, let's talk a little bit about the, it may come up. Let me go ahead and finish this up. Higher KVP does not generate significant scatter, misspelled, radiation in smaller body parts. Higher KVP does not generate significant scatter radiation in smaller body parts or in the lungs. Okay, higher KVP. It doesn't say extremely high, but higher KVP. Remember, because it is the body part itself, the thickness of the body, that's actually creating the scattering events. Number 2 says even in large body parts, KVP can be increased by 1 step of 15% without a substantial surge of scatter production. Number 3 says whatever small loss of subject contrast does occur from a single 15% increase in KVP is easily corrected by computer-based imaging systems. In other words, if you do lose that subject contrast because you stretch the scale out longer because you're using higher KVP, it does not really matter because there is a computer-based application that will be able to correct this for you. And finally, number 4 says higher KVP can ensure adequate exposure to the image receptor with minimum exposure to the patient. Higher KVP can ensure adequate exposure to the image receptor because it is pushing those x-rays through the patient. Pushing them through the patient, at least less of them are getting what? Attenuated or absorbed. I should say absorbed, so that they are going in and out of the patient, which is what we want to have happen during our exposure. Okay, on a sidebar, this is kind of skipping back over onto page 257. It says KVP is a minor factor for scattered radiation. This is page 256. It starts and it talks about obviously in the past when we were doing film screen, we were very, very cognitive of the issue with scatter, because scatter definitely fogged our images, which is what you're taught now, that it puts this blanket of darkness over all the entire image. But this experiment here shows you that with small body parts, like with the elbow, the two different 90, it says small body parts are not fogged at very high KVPs. The second elbow, B, was actually done at 94 KVP. There is absolutely no scatter. Notice there is a change in your scale of contrast. You can see the soft tissue is starting to darken a little bit. And then it says the right, even this is a large body part, a single step increases the KVP, did not result in significant fogging of the image for abdomen B. Again, you can see that there is a slight change in the scale of contrast as we look at the psoas muscles, and the pelvic wings itself are a little bit darker. So you are shifting your scale of contrast, but it's not enough to not use the 15% rule to help reduce patient exposure by 1/3. I'm on page 256 again. I am looking down towards the bottom of the first column. It says a lengthening of the grayscale can be seen in these images, demonstrates more details in the thickest bones, but no fog is present from scatter radiation. This demonstrates that high KVP does not bring with it any significant increase in scatter radiation when the body part is not large enough to produce substantial scatter in the first place. Scatter radiation originates primarily from large body parts and large field size, not from KVP. That's on page 256, a very important statement. Bottom of the first column carrying over to the top of the second. And then it says, second, even when scatter radiation is produced by the tissue with substantial quantities, KVP is only a minor contributing factor. So this allows some flexibility in adjusting KVP upward, even on scatter-producing body parts such as the abdomen. It tells you again to look at these images on page 257. Optimal KVP, with digital imaging processing, all barriers to the use of high KVP techniques, real or imagined, have been removed. There is simply no reason to keep KVP at previous levels. As a profession, radiographers have an opportunity here to lower radiation dose to the public, and for professional reasons, we are actually obligated to do so. Our job is to produce diagnostic quality images, and at the same time protecting our patient from unnecessary radiation. Here's your first step towards that. This is the very first step that we can do across the board, is that we can start increasing our KVP by incrementals of 10 for our body parts. Looking at those two charts again, you should familiarize yourself more with the one on page 258 because you are in the digital age. Table 16.3 on the next slide presents recommended optimal KVPs for using a minimum of 1. So I'll go ahead and show you that again, that is at table 16-3 on page 258. And compare it to the one that table on 16.1, and you will see that there is an increase in 10, incremental changes of 10 actually is the quick thought process for technologists. If we're wanting to do a reduction of our mass, we quickly add 10 to our current KVP setting, and we're able to reduce our mass by 10, give or take a few numbers, and there's a reasoning for that in the book. Again, I encourage you to read your book, but that was the gist of that. So even with film-based system, it is possible to make an across-the-board 15% increase in KVP and cut all mass itself into half by a standard technique chart and spare radiation exposure to the patient. This is on page 258, I'm sorry. Second column, with digital imaging processing, all barriers to have the use of high KVP techniques, real or imagined, have been removed. There is simply no compelling reason to keep KVP at previous levels. As a profession, radiographers again have an opportunity here to lower radiation dose, and that's exactly what that slide said. So to wrap this up, it says, therefore, we can define the optimal KVP as that KVP well above the minimum. Remember what the minimum KVP is, required for sufficient penetration, which strikes an appropriate balance between saving patient exposure and preventing excessive scatter radiation at the image receptor's plate. Based upon this definition, and we're talking about the optimal KVPs, are strongly recommended for daily clinical use in the digital age. So this chart here, you should start committing this to memory here. Other imaging qualities like mass, KVP is an electrical force. This is, where is it at? It's in here. Yeah, on page 258, on the bottom of the second column, it's got a little wrap up here. It says, light mass, KVP is an electrical force. We have mass being the what? Quantity, the number of electrons, the KVP being the force of how fast the electrons are moving. So they're both electrical components. They're not geometrical factors. Therefore, KVP has no bearing at all upon the recognizability functions. Go back and study that chapter. Remember recognizability functions of an image. How well can we tell what the image is? Recognizability. It has no impact upon sharpness of recorded detail, magnification, or shape distortion. KVP does directly impact exposure level at the IR, subject contrast in the remnant beam striking the IR, and noise level, both scatter radiation and quantum model at the IR. And that is the end of chapter 16, guys. Hopefully, I want to say that this is going to be better for you, small incremental bites. I do want to tell you that it's really important that you read the summary, read your chapters. If you have any questions, please set up an appointment with me. All you need to do is shoot me a text message. Shoot me an email and ask me or tell me what time you can meet or need to meet with me. If you have questions, I'll be happy to do that for you. We will do some Q&A. I think we're going to do it this Thursday. So we'll be doing some Q&A. Anyway, guys, I appreciate your time. I hope everyone is still staying healthy and safe. And if you need anything from any of us, please let us know. I appreciate it. Y'all have a good day. Thanks.